So we have finally come to the last result of this chapter, and that is proposition 117. So let's see the statement. Here we have a ring homomorphism F from the ring A to the ring B. Let us consider an ideal I of A and an ideal J of B. Then the following are true for I and J. Well, the first two statements, the third one is a bit different. So the first statement itself has two parts. The first part is this: the contraction of the extension of I contains I within itself. Let us take a moment to see where this ideal is lying. If you start with I, means basically you are inside A. I is after all a subset of A. So to I you are applying this extension operation. So the extended ideal IE will lie in B, to which you then again are applying the contraction operation. So that will get you back to A. That means this IEC is after all an ideal in A, and that contains I, that is the claim. The next one is about J. The extension of the contraction of J is contained inside J this time. You can run a similar argument here with J to see what's happening. If you are starting with J, means you are starting here. So first you apply the contraction operation to J, that will get you to A. That means inside A, JC is an ideal in A, to which when you again apply the extension operation you get back to B. So this JCE is an ideal in B, and that the claim is that it is inside J. That's the first part. The second one is a bit more complicated. Here we take one more step. The contraction of the extension of the contraction of J is equal to the contraction of J. This means that if you interpret this as an operation that you are applying on JC, because if you look at the right hand side, you are first extending and then contracting JC. Then you do not get anything new, you get JC back. And the second one is about I. The extension of the contraction of the extension of I equals the extension of I. You see in the text how these statements have been proved, and if you have any doubt regarding these proofs, you write in the comment section below, because from now on we are not going to cover proofs that are available in the text. And let us now finally see this third part. If C is the set of all contracted ideals in A, what does that mean? It means that we are considering all the ideals in B, and then we are contracting each one of them. Those contractions are all going to lie in A, they will be ideals in A. The collection of those contractions is C. Similarly, we are also considering E, which is the set of all extended ideals in B. What does that mean? That means we are starting with all the ideals of A and we are considering their extensions. Those extensions are all ideals in B, and their collection is this E. Then, if so, then C equals this and E equals this. C is the set of all ideals I in A such that IEC is equal to I, and E is the set of all ideals J in B such that JCE is equal to J. This I is not exactly that I, and this J is not that J. If you want, you can use some other letters here. There also I and J were just some ideals. That's not a very big problem. So these things have to be proved. Already it's available. And then what is the relation between these two sets, C and E? You consider this mapping, which is a function from C to E, which takes an element I from C and maps it onto its extension. Turns out that that is a well-defined mapping from C to E. To prove that, actually you have to show that for any I in C, IE is actually inside this capital E. And you can guess that part 2 has a role to play in showing this. So once that is done, then the claim is that it's not just a function, it's a bijection from C onto E. It's the one-to-one onto function. So being a bijection, it will have an inverse function, and that inverse function actually does this. It takes any element from E, of course, its inverse means it will map E onto C. So if you choose any J from E and apply the inverse function to J, you get the contraction of J. Okay, so that is the entire thing. So in this way, these operations of extending and contracting ideals relate the ideals of A with the ideals of B in a fairly nice way. So I urge you to go through the proof and make sure that you understand everything. If you have even a small doubt, you write in the comment section below, and I will try my level best to clear it up. Besides this proposition, we still have an exercise within the chapter itself, not the chapter end exercises. Those are all there, okay, we have to solve them. But even before those things, there is an exercise, and it has some parts. So next week we will start solving those parts. We won't be able to solve all the parts in one video, but in 2 videos I think we can do it. So see you next week with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.